In this video, we're going to cover our very last section, 9.2, and it's going to be on the dot product and some of its applications. And so all the dot product is, and to define it, we're going to look at these two vectors here. And is what we'll do is we'll multiply their horizontal components. So I'll have A1 times A2 plus, and then we'll multiply their vertical components. So it's B1 times B2. And so that right there is the dot product. And it just seems like some new random operation, but again, it will have some interesting applications to it. And we'll see one here in a few minutes, but let's begin by just practicing finding the dot product. Okay, so here's our first example. We have these vectors u and v. And so one of the things we're being asked to do here is to just compute the dot product of u and v. So I'll take, again, the horizontal components and I'll multiply them. So I have 2 times 3 here, plus, and then I want to multiply the vertical components. So I have a -1 and then a +1. And so let's see what we get. If we add those up, right, we have what this is 6 minus 1, so that's 5. There we go. Let's try another one of these out. Let's try this 5 times v and then dotted with u. So the first thing I want to do is actually compute 5v. And so we know how to multiply scalars by vectors. We just are going to multiply each component of v by 5. Okay, so I'll have 5 times 3 here, so it's 15. And then 5 times the vertical component, so that's going to give us a 5j. Okay. Now we can go in and we can compute 5v dotted with u. Okay. So let's write in our work here for that. So I have this 15 that I need to multiply with this 2 up here. So it's going to give me a 30. All right. And then let's look at the vertical components. So we have a 5 and a -1. So that's actually going to give us a -5. And right, that's going to simplify to 25 there. All right, so there's a couple examples just computing our dot product. Let's go ahead down here, and we're going to see that the dot product can be used also to help us find the angle between two vectors. Okay? And so we're going to try to find the angle theta in between these two vectors, v and w. But to do this, we're going to introduce a third vector. Okay? And this third vector here, let me use the line tool here. Here we go. Right, so that's pretty close. So this vector here, I'm going to call it u. Okay. And this vector u, we can say something about it. We can say that w plus u is equal to v. Okay. So let's kind of write that down here now. Let's see. I'm going to say since, let's do u plus w is equal to v. Okay. That's what we can see in the picture. I'm going to have us actually solve this for u. It's not clear why yet, but this u is going to be helpful to us. So if we start solving for u, this is just going to be u is equal to v minus w. There we go. And we know what v and w look like. They look like this. So that means that I can actually rewrite this v minus w if I wanted to. I could write it as what, a1 minus a2 I, and then plus b1 minus b2 j. There we go. All right. Now, this part that I've written right here. This is going to become helpful to us later on. So we'll just keep this in mind right here. And is what I want us to do next is consider this triangle that we have here. And if we were to think about it, like the magnitude of this side would be the length of that vector, okay, right? Or the length of that side. Okay. The magnitude of this vector would be the length of this side. The magnitude of this vector would be the length of this side. Okay. And we have this one angle here. Okay. And so is what I'm getting at is maybe we have a trig equation that we can use, or an equation that involves trig, so that we can relate maybe these sides and that angle. Okay. And we do have a rule or a law that we can use here. We can use our law of cosines. So I'm going to write in here our magnitude of u squared is equal to the magnitude of v squared plus the magnitude of w squared minus 2 times the magnitude of v and the magnitude of w. There we go. And then cosine of the angle between v and w, which is theta. So this is helpful now. We have introduced theta into this equation, right? And as I mentioned, our goal is going to be to find this angle theta. Right, but there's actually more we can do here. So we can actually find the magnitude of u and v and w, and we actually get some really nice cancellation if we do that. But it's going to get really messy here for a moment. So remember, u is this vector here. And if you find the magnitude of a vector, right, you square each component and you add those together, and then you take the square root. Okay. Well, we're going to look at the magnitude squared. And so that square root and the square are going to undo each other. So all I'm going to end up with is each component squared as I go to compute this. So let's go ahead and see what that looks like. That's going to look like a1 minus a2 squared plus b1 minus b2 squared. Okay. So that's the magnitude squared of u. If we do the magnitude squared of v, okay, remember v is this a1i plus b1j. So its magnitude is just going to be a1 squared. And just to make it clear here, I think I'm going to put it in parentheses. a1 squared plus b1 squared. Okay. And then if we find the magnitude of w, w is a2i plus b2j. So again, its magnitude squared is just going to be a2 squared plus b2 squared. And then we have minus 2 times, again, the magnitude of v, magnitude of w. These ones I'm actually going to leave as is. These are actually going to be part of the formula that we'll have in the end. But as I mentioned, a lot of things should be canceling here shortly. Okay. So is what we're going to do is we're going to expand these out. Okay. And then, like I mentioned, a bunch of things will cancel. So let's do that. So we'll have our a1 squared. Okay. We'll have a minus 2 a1 a2, and then a plus a2 squared, and then a plus b1 squared minus 2b1 b2 plus b2 squared. And then this is all still equal to all this stuff over here on the right. And so I think I'm going to make my life a little bit easier and just copy this over. And I think I'm going to have to zoom out so that we can actually see what cancels. There we go. Okay. So let's see. I think I'll just use a yellow marker here to write what cancels. So we lose our a1 squareds. If we subtract by a2 squared on each side, we'll lose those. The b1 squareds, the b2 squareds. And so you'll notice also that everything that's left has a -2 attached to it. So I could also divide each side by -2 here. But maybe I'll save that for the next step. Maybe we'll just write what we have here. So we have minus 2 a1 a2 minus 2 b1 b2 is equal to just this stuff right here. This is all that's left on the right. So let's zoom back in. So if we divide each side by -2 here, we're going to get an a1 a2 plus b1 b2 is equal to the magnitude of v times the magnitude of w cosine theta. And this right here should look familiar. This is our formula for the dot product. So what this means is that v dotted with w could also be computed using this little formula right here. So we're actually getting a kind of a bonus formula here. We're going to get two formulas in one. So this is one way, again, or a second way, maybe I should say, that you can compute the dot product. Okay. As you could find the magnitude of V, find the magnitude of W, multiply those things, and then multiply by cosine of the angle in between them. Okay. That would give you V dotted with W. Okay. But this isn't what we were looking for. We were looking for the angle between these two. So I need to do a little bit more work here. And I was just debating where I have room to do that. Maybe we'll just finish this up here at the very bottom of this. So to start solving for cosine or theta, I'm going to divide each side by the magnitude of V and the magnitude of W. And so if we do that, we're going to wind up with cosine of theta is equal to V dot W divided by the magnitude of V and the magnitude of W. Okay. And then finally, we can solve this for theta. We can use cosine inverse. Okay. And just so that I have it maybe right below this formula here, I just scooted that over. So we have cosine inverse of, again, V dot W all over the magnitude of V times the magnitude of W. There we go. And I'll go ahead and I'll box this one here too. There we go. And so I have these on the next page. Okay. These were the two formulas we were looking for. So again, we have a formula for doing the dot product, and we have one for finding the angle in between two vectors. And it's actually really convenient that we're using cosine inverse rather than sine inverse or tangent inverse, because cosine inverse can actually give us angles from 0 to 180, while tangent inverse and sine inverse cannot. Okay. And so when you use this formula, it will always find you the smaller of the two angles in between two vectors. For example, if we had this vector here and this one here, the angle that this formula would find for you would be this one. Okay. Because do note that there is another angle over here. There we go. All right, well, let's try this out. So we have the vector v, which is equal to minus 2i plus 5j, and w, which is equal to 3i plus 6j. And we're going to find the angle in between them. Okay. So if we are going to use this formula here, then we need the magnitude of v and w, and we need the dot product of v and w. Okay. Let's start off with maybe our dot product. All right, so what we have minus 2 times 3. So it's going to give us a minus 6. And then a 5 times 6, so that's 30. So this gives us 24 for the dot product. There we go. Now we need our magnitudes. So we need the magnitude of v. So if we square 2, that gives us 4. If we square 5, that gives us 25. So this comes out to the square root of 29. We do the same thing with w. We want to square 3, which is 9. Square 6, which is 36. All right, and so that's going to give us what here? That's going to give us the square root of 45. There we go. And so now we have everything we need in order to find this angle. So let's do that. So I'm going to have theta is equal to cosine inverse of v dot w over the product of the two magnitudes. And while we're at it, let's go ahead and plug this into the calculator. Here we go. So first of all, I want to make sure that I'm in degrees. So let me come down here and I'll do just that. And this is because typically when we're thinking about the angle between two vectors, we're going to typically want to be in degrees rather than radians. Okay. So now that I'm in degrees, I'll hit cosine inverse here. We have our 24 divided by the square root of 29. And I need to also multiply that by the square root of 45, which means I'm going to need an extra set of parentheses here, which I'll just insert here in a moment. Okay. I want to make sure that we divide by not just the square root of 29, but also the square root of 45. There we go. And then one last parenthesis. Okay. So it looks like we're getting here about 48.4 if we round to one decimal place. we go. All right. So the next thing that we're going to look at are parallel vectors. Okay. So we know what it means when two lines are parallel, but when two vectors are parallel, this can happen in two ways. The angle between them could be 0 or it could be 180. Okay. So in other words, the two vectors could be pointing in different directions. And by different directions, I should be a little bit more specific and say the exact opposite direction. Okay. So those would be parallel. Okay. They don't have to be the same length. Okay. I did sketch them the same length, but also the more obvious one would be if they are pointed the exact same direction, they are going to be parallel. There we go. All right. And another thing that we might talk about when it comes to vectors, other than them being parallel, is we might talk about them being what we'll call perpendicular or sometimes orthogonal. Okay. You're actually going to see perpendicular more often than orthogonal, specifically because perpendicular is going to be referring to um, two vectors in 2D having a 90-degree angle in between them. Orthogonal is a more general version of the word perpendicular. It could refer to higher dimensions. Okay. So let's say that these are our two vectors here, v and w. Okay. Then we need a 90-degree angle between them if they are to be perpendicular. Okay. But there is something interesting that happens here. Okay. Let's think about our dot product formula. So remember, v dot w could also be computed with the magnitude of v times the magnitude of, what do I have here? V and w. Okay, so magnitude of w, and then cosine of the angle in between them. Okay. And so I want you to think here for a second, what is cosine of 90 degrees? Okay, well, that's 0. So is what happens here is we end up with v dot w being 0 if the two vectors are perpendicular. Okay. And we'll record that here on the next page. Okay. All right. So yeah, two vectors v and w are perpendicular if and only if their dot product is 0. All right. And so let's take a look at an example. So if we're trying to determine if two vectors are perpendicular, all we need to do is take the dot product. If it's 0, they're perpendicular. If it's not 0, they're not perpendicular. Okay. And additionally, we could check to see if they are parallel, right? It mentions that maybe these are parallel. So we could find the angle in between the two vectors in that case and see if it's 90 degrees. Or sorry, see if it's 0 degrees or 180 for parallel. Okay. But the nice thing here is if we are going to check if they're perpendicular or parallel, in either case, we're going to need the dot product. Okay. But if the dot product comes out to 0, we're done, and we don't need to worry about actually finding the angle between v and w because we'll know it's 90. Okay. So let's go ahead and do just that. If we find our dot product here, what we have 3 times -8. And then we have what, -4 times -6. And so that is -24 plus 24, which does give us 0. And so that means that v and w here are perpendicular. There we go. All right. So another couple applications. that we could talk about are projections. Okay. Here we have a picture of a scalar projection of V onto W. And I want you to think about this projection like a shadow. Now, is what's going on here is you could imagine that maybe we have some light source up here and it's causing this shadow. Okay. And I do want to note that when we do make these projections, we want this dotted line I've made to make a 90-degree angle with this vector W here. Okay. But the shadow that's made is this part right here in the picture. Okay. And again, this is the shadow of V onto W. Okay. And we'll call this the scalar projection of V onto W. Okay. But it ends up that we can actually find this length here if we'd like to, okay, which is again the scalar projection. And so all we would need to do that is think about, well, do we have some way to relate this side here, okay, and maybe the vectors v and w in any way. Okay. Well, I'm kind of noticing that the vector v and this projection are forming a triangle. And so if we maybe use cosine theta, that might be helpful. So cosine theta, right, is adjacent over hypotenuse. So that adjacent side is the projection that we're trying to solve for. And if I divide by the hypotenuse, it's just the length of v. Okay. And so we could maybe multiply both sides by the magnitude of v here. And we'll have that our projection of v onto w, our scalar projection, is then equal to the magnitude of v times cosine of theta. There we go. And maybe we could do a little bit more with this. Okay. For example, and it's not going to be obvious what I'm about to do here, but I'm going to multiply by something here. I'm going to multiply by the magnitude of w over the magnitude of w. So I'm just multiplying by 1 here, but this is going to end up being pretty helpful. Okay. So let's scoot this down a little more. All right, so if we go ahead and combine this into one big fraction here, we'll have the magnitude of v times the magnitude of w cosine theta divided by the magnitude of w. And I'm going to scoot this down a little bit. Okay. And if you look at the top here, that v, the magnitude of v times the magnitude of w cosine theta, that's just the dot product of v and w. So for my final formula that I'm going to write up here, I'm going to write v dot w divided by the magnitude of w. So that's how we'll compute what we'll call the scalar projection. Let's go on to what we'll call the vector projection. All right, so our vector projection of v onto w, this is going to be a vector that actually has the same length as the scalar projection, but it's going to be a vector rather than just a length. Okay, and it's going to point in the direction of w. Okay. So we actually are pretty much almost there since we already have the scalar projection. This isn't going to take us much work. Okay. So the scalar projection is going to give me the length that I'm looking for. Okay. And so we found that to be, if we come back up here, right, V dot W over the magnitude of W. Okay, and so remember, this is just a scalar here. And I want to multiply it by a vector. Okay. And specifically, I want that vector to be pointed in the direction of W. Okay. And it would be really nice if that vector was of length 1. That way, when I multiply it by this, it's the length of the scalar projection. Okay. And so we can do this really easily. We can just multiply here. I'm going to maybe put this in parentheses. I'm going to multiply this by the mag of W over the magnitude of W. And since that's just all multiplication, well, I should be a little bit careful about how I word that. Um, since we are multiplying here, though, and this magnitude of W and magnitude of W are both scalars, we won't have any issue putting those together here. And so I will do just that. I'm going to rewrite this now as V dot W over the magnitude of W squared. And then I want to multiply this by the vector W. So again, this is all scalars in here. After we dot V and W. So this is a scalar times the vector W. Okay. Well, let's go ahead and try to use this. Okay. I'm going to have us try to use the formula for the vector projection of V onto W, and then we'll look at an application for the scalar projection. Okay. And so I've started some of the work here for us already. We were going to need the dot product, and we were going to need the magnitude of W. Okay. Right? This formula has both of those things in it. Okay. So let's start to write down. Oop, let me come back down here. There we go. All right. So, yeah, we were looking for the projection of V onto W, which should be the dot product of V and W over the magnitude of W squared. So it's just going to be a 5. Maybe I don't need this big of a parenthesis. There we go. And then we wanted to multiply that by the vector W. And so this just gives us what 8/5 I plus 4/5 J. And so that right there, this is our vector projection of V onto W. All right, let's go ahead and take a look at an application of our scalar projection. So when it comes to work, it ends up that we can relate this to these projections that I'm talking about. Okay. And let's read the definition here. But this is really kind of a one dimensional definition. It says the work done by a constant force of magnitude F on a point that moves a displacement D in the direction of the force is the product of that force times the displacement. Okay. And now that's just the magnitudes because, again, this is kind of one dimensional. Okay. Now, if we then suppose, well, what happens if these things are pointed in different directions? The force and the displacement don't need to be pointed in the exact same direction. Okay. So, is what we'll do is we'll just figure out, and actually, Check, 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 check. Check, check, check. So the question is, what do we do if the force and the displacement are in different directions? Okay. So here's what we'll do. Okay. Is we'll figure out how much of that force is in the direction of the displacement. Okay. And that is just simply the scalar projection of F onto this displacement vector. Okay. So let's go ahead and recall what our formula would be here. So if we were to look at the scalar projection of F onto D, okay, this should be equal to F dot D divided by the magnitude of the displacement vector. Okay, there we go. Okay. And we can do a little bit more here, right? So this is just how much of that force was in the direction of the displacement. I need to still multiply by our displacement. Okay. And specifically, I mean the magnitude of our displacement. Okay. So our work is really going to be, okay, again, the force that is in the direction of the displacement. Okay. And then multiplied by the magnitude of the displacement. Okay. So this is really still force times displacement. It's just since they're not in the same direction, we're just taking the amount of force that is actually in the direction of the displacement. Okay. And we can simplify this a little bit further, though. You see those magnitude of D's cancel. And so we end up with W is just equal to F dot D. And remember, you can write the dot product also in a different way, right? So that you could also write this formula as the magnitude of F, magnitude of the displacement, times cosine of the angle between the two vectors. Okay. And so these are going to be our two work formulas. And for those of you who wind up taking physics in the future, you're going to be um, computing work or using work to solve problems all the time in the near future. Let's try one out here. Okay. So this says a wagon is pulled along level ground by exerting a force of 25 pounds on a handle that makes an angle of 38 degrees with the horizontal. How much work is done by pulling the wagon 100 feet? Round your answer to the nearest foot pound. Okay. So they've actually already given us the magnitude of the force, the magnitude of the displacement. Okay. So the magnitude of the force is that 25 pounds. The magnitude of the displacement is the 100 feet. And they've given us the angle between the two vectors. Okay. So all we really need to do is multiply the 100, the 25, and cosine of 38, and we're done. Okay. So our work here is just 100 times 25 times cosine, again, of the angle between them. Okay. And so let's see what that gives us. So we have 100 times 25 times cosine of 38. All right, so that's giving us about 1,970 here. Right. And we could actually write down our units here. These are in foot pounds. Right. And so this here wraps up the dot product.